You know, the best way to learn something is to be able to teach it yourself. So I'm trying to prepare for some of my finals by doing some problems and, if you find any use out of it, that's good. But I don't know. This is mostly for my benefit. Anyways, we have this differential equation here. We want to solve it. Um, and th this is kind of easy money. So let's try to do this pretty quickly here. We have that the variation of parameters formula will give us the solution for this non-homogeneous equation here. Notice that this is NH, non-homogeneous, because it has this tangent part on the right-hand side that's not zero. So we're given that the variation of parameters states that the non-homogeneous um, solution will be x of t plus big X of t, or equals big X of t, big X of t plus integral t naught to t of big X of t, x inverse of s, fs, ds. And this is in general for any system in Rn. Um, this can get a little bit complicated, but from the this inverse here, we can kind of simplify this down in this example because this is only second order, so we don't actually need to apply this particular formula. We can use one of its variations. One of them that is adapted for R2, which is what this is going to be in since it's second order. So we can see that this solution is actually going to be, oops, let me get my drawing here. This solution is actually going to be something like x of t equals c1 phi 1 of t plus c2 phi 2 of t. It's a theta. We draw phi there. Phi 2 of t plus integral from t naught to t of f of s over the Wronskian of s times this whole thing here. This negative phi 1 of t, phi 2 of t, phi 2 of s rather, plus phi 2 of t, phi 1 of s ds. Um, What do we get this formula? Well, I mean this inverse here. If you remember, there's kind of a basic formula to find the inverse of a 2 by 2 matrix. Um, so in this example right here, we have a 2 by 2 matrix. If we were to convert this to a system, um, so this is just coming from the 1 over the determinant times the I think you make it like you flip the a and the d values and then make the other ones negative, I think, to get the inverse of a 2 by 2. So that's where this part's coming from. Um, so this will be right here. This is the solution to the homogeneous equation, x double prime plus x equals 0, um, which we can solve by finding the characteristic polynomial, r squared plus 1 equals 0 there from the order of the terms. We see r equals plus or minus I, and using the Euler property, we can write the solution to this related homogeneous equation right here. It's going to be x of t. Actually, I'm going to write this as h so we can not get confused here. H of t equals c1 cosine of t plus c2 sine of t. Yeah, and you can verify that if you want. This is just from the Euler property of converting from this. This is going to be the eigenvalue of the system matrix, and we can convert that to the real plane by using the sine and cosine property. I think that's the Euler formula. All right, so that's this part right here. So let's start writing our solution here. We have x of t equals c1 cosine of t plus c2 sine of t. And we're going to or add that to this integral here, this t naught to t. F of s is, the f is going to be this tangent of t part right here. So that's f of t. So we can put that on top in terms of s there. We're using s's because we already have t's in this part. We're going to need to, when we evaluate this, we're going to need to, um, I guess, have something to plug in. So we just use a storage variable, which is s here. So we have f of s is tangent of s then. Um, and this Wronskian we get from the solutions of the homogeneous part. Let me just go off to a little side here to get the Wronskian. The Wronskian W of t is going to be the determinant of the solution matrix of the homogeneous part. So the homogeneous part of the homogeneous solution, we see this the C1 part. Um, it's cosine of t plus sine of t, cosine of t, sine of t, and the second row of this matrix will be the derivatives of those. So we see minus sine in the bottom of this one for the derivative of cosine, minus sine of t. Derivative of sine is cosine, so we have cosine of t right here. And this determinant is going to be equal to cosine squared, cosine squared of t, minus the negative sine squared, so plus sine squared of t. You see that that's just 1. So what we can say here is this is just over 1. Perfect. These 5 values right here, those are the same thing we use to plug in the Wronskian. They're the linearly independent solutions of the homogeneous part. So phi 1 is cosine. So we see that this is negative cosine of t. This next part will be sine of s. I'm just plugging in the corresponding parts of this equation here. Sine of s plus sine of t, cosine of s, ds. And this is our general solution right here. I think we can simplify this a little further, so let me do that. X of t equals c1 cosine of t plus c2 sine of t. And then let's see here. So what we can do is, so obviously that 1 is going to go away in the denominator there, but it looks like we can, this tangent is sine over cosine, so it looks like we can kind of distribute this tangent and cancel some terms here. Now we'll get, let's see here, so we distribute that. We get sine squared, or minus sine squared, minus sine squared. I'm just distributing this. The cosine cancels. Minus sine squared of s. Yep. Yeah, I remember not to. Oh, you know what? Actually, I can't cancel that, right? Because this is a t, not an s. So I think once we simplify this part, we're going to get sine squared of t, cosine of t, sine squared of s rather. I'm all messed up here. Sine squared of s, cosine of t, and then we have a cosine of s in the bottom because of the tangent. Cosine of s, and then I think this part would cancel a little bit nicer. So distributing this tangent here, we see that we can have yeah, because there will be a cosine s up here in this part right here, and then there will be a cosine and a cosine of s in the denominator, this tangent part. So we can just say that that will be sine of t, sine of s, I believe. Yeah. ds. And this will be our general solution. and I don't want to integrate that. That looks horrible, so I'm just going to leave it like this. And honestly, this is probably um, a better answer because you can kind of see the parts a little bit more clearly than if it were all the way expanded. Okay.